Let's start. So today's topic is called Propositions as Types. We're going to make explicit a correspondence which we have been using already in Agda all the time while working with Agda, with logic. But today we're going to have a look at it from sort of a bird's eye view to understand what is going on, what this correspondence is. And I think it will also be useful in some of the projects, especially anybody working on logic. If your project is about logic, you will, I think you will find this useful. But I think more importantly, this is a very fundamental correspondence in foundations of mathematics, which is interesting in its own right. And so I think it's worth looking at it. Now, before I go to this central topic of propositions as types, I would like to just quickly revisit the one point about the semantics of propositional logic, which we did last time, also just to warm up, but also because that part of the lecture didn't get recorded, the audio didn't get recorded. And so this is my way to compensate, but also to just review a couple of things that happened in the exercises. So remember last time we were doing the propositional, so the Boolean semantics, like this. The Boolean semantics of the propositional logic. And there, so the propositional part means that we had atomic formulas, and then we have the connectives. And if we excluded middle, once we did that, this is called the classical propositional calculus, the classical logic. And we said, okay, you can interpret this stuff in the Boolean algebra which has two truth values, which I could write 0 or 1, or I could use these two symbols, but these are the semantic values and these are just symbols. And let's remember, how did that work? The theorem that I wrote down was the one that you might have heard in class somewhere, which said that phi is provable. So phi is provable if and only if phi is a tautology. So phi is provable means that we get a proof of the statement that under with zero hypotheses, we can prove phi, and so there's going to be some derivation here, some tree showing how phi is provable. And phi as a tautology means that when you look at it as a map, so remember the map takes an assignment of truth values to atomic formulas. So capital A was the set of atomic formulas, and for each formula we get a truth value, whether it's true or false, and then depending on that we assign a truth value to 2, and so for this to be a tautology means that it's constantly true. Is constantly true. That's the theorem that you want to prove, and let's also remember that in this direction it's called soundness. It's soundness of logic. And in that direction, it's completeness of semantics. Of Boolean semantics. Okay, these fonts are getting ridiculously small. Anyhow, now here's my point. When you're proving this theorem, and this is going to happen a lot in your projects, you're going to have a theorem that you want to prove. And then you say, how am I going to prove? Like, for instance, soundness. That which goes in this direction. And you did this in the exercises, by the way. You proved soundness there in the exercises. But let's consider what happened. Okay, so you say, okay, I want to prove the direction from left to right. How am I going to do this? You say, well, Phi is provable means I have a derivation like that. What could I possibly do? And then you say, I'm going to do induction on the structure of this derivation. So I will say, aha, I'm going to have an induction argument where I can make inductive hypotheses that structurally smaller derivations, that is to say sub-derivations, already satisfy the desired property. Whenever your plan of attack is that you are going to have an induction argument that is on a derivation, and that is going to happen in your projects, then typically what happens is that the theorem that you want to prove is not actually the one that's going to work for your induction argument. That is because almost always the theorem, the final theorem as stated, has a special form. It's actually a special form, but when you start working on your induction, it will quickly turn into a more general form, and then because it's in the more general form, you need to now know what to do with this general form. So in this particular case, what is special? Well, the special thing is that there are no hypotheses. It's with empty hypotheses that we're stating this. So this is not the most general form of a derivation. So imagine that phi is actually an implication. Well, if it's an implication and you use implication introduction, one line above, you're immediately going to have an extra hypothesis. And so then your theorem just doesn't apply anymore because it only applies to things in the empty context. And this is typical, and it comes in many facets. It happens all the time in these sorts of proofs. Also, when you're proving, say, a property of a programming language or some other kind of semantics of some other kind of language, this happens often. So that is the difficult part. That's where you actually need to think about what is going on, because you have to be able to state the correct generalization of the theorem. Once you manage to state the correct one, usually the induction works very nicely. So if you're getting stuck on the induction steps, that means that it's very likely that what you're proving has not been correctly generalized or needs to be generalized in some other way. And it's a game of balance. If you don't generalize, then your induction hypothesis, then you won't be able to do it. If you try to make it too strong, then again it's not going to work well. Because, why is that? Because the conclusion that you're trying to prove is pulling in one direction. Okay? The easiest conclusion to prove is true. But the hypotheses are pulling in the other direction. The most useful hypothesis is false, because from false anything happens. So you have to find a good balance between the two that makes the loop go through. And so then the correct generalization, as you might remember from the exercises, was you immediately have to ask, aha, when I do my induction hypothesis, when I do my induction, what will it look like when I'm in the middle of it? Well, when I'm in the middle of it, not just in this final form, I will have hypotheses. So that means I should phrase the theorem in the most general form. The most general form is that you say, aha, I derived something under hypothesis, and then the theorem has to be if this, then, well, then what? now something, but now it can't be just about phi, it has to be about size as well. Yes? And so in the theorem that there was then, for all eta, so for all evaluations, so this is evaluation, remember, evaluation, which assigns truth values to atomic formulas. For all, something happens, and the thing that needs to happen is that if you look at the truth values of the hypotheses, and you take their conjunction in the Boolean algebra, of course. So now one of these things here, let me make remarks here. So what is this? Well, one of these things is an element of 2. And this is conjunction in 2. Right? This is conjunction in the Boolean algebra 2. So the truth table, true. No? So this needs to be smaller than the meaning of phi at that same evaluation, where smaller means, of course, that bottom is below top, right? That's how it's ordered. That's the order that you use. And so why is this a generalization? Because let's look at what we had here. Here we had the empty context. So if this is the empty context, what is the empty conjunction? The empty conjunction is the neutral element for conjunction, which is true. So when n equals 0, when there are no hypotheses, when n equals 0, we need to replace this with true. So then it would be that t is less than phi of eta for all eta from a to 2. Well, but you know, if the truth value is always greater than or equal to true, then it's actually constantly true. There isn't another truth value above true. So this is the same as saying that it's greater than true is the same as saying it's equal to true. So it's precisely the special case that we get. Yes. This is a game of mastery and artistry. To get this induction hypothesis correct, this is going to be sometimes this is the hardest part of the theorem. Once you get it right, then the induction just goes bloop. Okay. Now, this is for classical logic. What about intuitionistic logic? Well, for intuitionistic logic, so no excluded middle, we need to use Heyting algebras, which are the corresponding structure that is like the Boolean algebras, but without the nice properties of complement. And I'm not going to go into that. A typical Heyting algebra is the topology of a space. So topologies of topological spaces are Heyting algebras. They're more than that, they're nicer than that, but to give you at least some examples of where they arise from. And it's more complicated, and we're not going to go there, because this is relating logic to algebra. But I want to do something else. I want to relate logic to computation. Logic has many facets, and this is the algebraic one, but we're going to go in the direction of logic and computation. So for that purpose today, I'm now first going to more carefully review the computation part. We learned, we did say we did explain things like inference rules and inductive data types, and you've been using Agda, and so you understand that in Agda you can prove things, but you can also compute things, and it's kind of a programming language. But let's make this precise, and let's first formulate a fragment of type theory, which is really a simple functional programming language, and then we will see how it relates to the intuitionistic propositional calculus. And so the thing that we're going to review here is called simply typed lambda calculus. This calculus is the basis for many programming languages, and proof assistance, because it is the essence of functional programming, so to speak. In the lecture notes, which are somewhere here, I have included, so there's lots of reading material here that I recommend if you want to know more about this, and I recommend that you know more. I just recommend that you know a lot, okay? So that's usually pays off. You should know a lot, but you should also know when to speak and when not to speak, okay? The simply typed lambda calculus here is from some this is a review that I took out of some categorical logic notes that I wrote with Steve Audi a while ago. It's just one section, and it explains the simply typed lambda calculus in gory detail. So you can have a look at this, and there are examples and all of that. And just so you know that you're not short on reading material. And here, let's have a look at how we will do it. Just an overview. Okay, so why is it called simply typed? It's called simply typed to emphasize that the types we're going to use are not the dependent types that we have been using in Agda, but are simple types, which means a type is just like a thing that doesn't depend on anything. Like the natural numbers, for instance, is just a type, versus the identity type, where it depends on the x and the y that you're comparing. That's the meaning of simply typed. Lambda calculus, well, because they're going to be lambdas. Okay, so what is a simply typed lambda calculus? What is it made of? So we're going to, first of all, it is a formal system, okay? And it's a deductive system. So formal systems means I will give that, in principle, we give completely precise semantics, completely precise syntax and rules of manipulation of symbols. And in fact, you can do that. And I would recommend that if you really want to do that, then you implement it, right? Writing on paper something that is supposed to be completely precise is a losing game. You're just going to make a mistake. But even worse, nobody will care that you made a mistake. So if you really want to be completely formal, use a computer. The computer is going to get you, okay, when you make a mistake. So there will be several entities. These are also sometimes called syntactic classes of expressions. Two of them. There are expressions that are called types. By the way, I'm now giving you a description of the simply typed lambda calculus as a syntactic entity. But there is an important question of what does it all mean, and that means that's the chapter called Semantics, which I'm not going to touch on here. But if anybody is interested, there is of course also thick books about that. So there will be types, some expressions which are called types, and then there will be some expressions called terms. And so I have to explain how to form these expressions. So how do we form types? Well, a type, I will use letters A, B, C, and so on. I'm not trying to be completely formal here because I know that that is impossible until I implement things, but formal enough, rigorous enough, so that somebody who sees this has some idea of how you would implement it. So types, okay, so first of all, there is a collection of basic types or primitive types. So these go by different names. They're called primitive types, ground types. I think Americans tend to say that. Sometimes they're called basic types. And this is just some collection of stuff given. Like, for instance, it depends on what kind of lambda calculus you could have. For instance, you might throw in the primitive types Boolean and natural numbers or something. It really depends on each particular case. And then there are some constructions, and the constructions that we're going, okay, so we're going to have the unit type. That's a type. We're going to have the empty type. That's a type. Then we're going to have function types, product types, and sums, sum types. So this is how you can create types using this stuff here, plus whatever primitive types you have. Of course, these are intended to be what you think there will be, right? The type of functions, the type of pairs, the type of, okay? Then there are terms. And now the way that you deal with terms is, so terms, I will use letters S, T, U for terms. Here, there will be, first of all, some primitive constants. This is the stuff that we can throw in. For instance, if we throw in the natural numbers and the booleans here, then we might throw in the primitive constants 0, successor, false, and true. Okay? Then you go down these types and you look at what do you want, what will be, how will you make terms of each type. Oh, also variables, X, Y, Z, some collection of variables. Okay, and now we look at these types and say, how do you make a type? What do we do with unit? Okay, so there's going to be unit, which I'll write like this. Then there's going to be, there's no eliminator for unit. Now for empty, there is no introduction form, so no term to create an empty, but there is going to be a term that uses an element of empty, and I will call it absurd A, which takes a term. So it has this form, absurd A, and then of a term T. Okay, so this is how you're going to use T. If T is an element of empty, then absurd of empty will let you do whatever you want. Then functions, okay, what can we do with functions? We can have abstraction. Now when we have lambda abstraction, because this is a simply typed lambda calculus, it's typed, we want to put a type here. There are lots of variants of this calculus, but some have this type here, some don't. I'm doing a very explicit simple one where I tag each variable when it is introduced with a lambda is actually tagged. Okay? Then we can also have applications, so that just means I can apply one term to another, so this is called lambda abstraction. This is called application. Now I'm done with functions. Now I look at this and say, okay, so what about pairs? Okay, so we can make a pair. We can project out the first component. We can project out the second component from a pair. What can we do with this plus business? Okay, so there are two injections, which I'll write iota 1, iota 2, where you inject into a sum. And then there needs to be something about how you use this, and this is a case statement. So there will be different ways of writing a case statement. And let me just use a computer sciencey one, and it would go something like this. Case T of, if it is of the form iota 1 of x, then you do something called T1, or if it is iota 2 of x of y, then it's a T2. So this is how you'd write a case statement. You would say if T came from a sum, it's either of this form or that form. In this case, it's that in this case we have T1, in the other case we have T2. But this is also kind of nasty for writing rules. So sometimes people write things like case, and then here they might have like, I don't know, they invent all sorts of things. But one would be they invent, like they say it's a T, but then here they need to indicate the variable, so they might write something like this. Okay, you will see different notations, but anyway, it's a case statement. Okay, so far we have the syntax. Now, the next thing that you want to specify when you are defining a calculus, formal calculus like this, is again, what is your judgment form? In the propositional logic, we had the judgment form that said from such and such hypotheses, such a thing is entailed. We had a phi, phi1 dot 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 phi n entails psi. So now we need something else, and so now we will have two judgment forms. The judgment forms take the following shapes. Before I write down the judgment form, I will explain what the context is. Remember we already had context, but let's see. So typically we will write gamma or delta for these contexts, and a context is a list of variables. The last time we had lists of variables, but now because everything is typed, it's a list of variables with their types. So like this. And the xi need to be distinct. You can't repeat them. So mathematically speaking, this is a map which takes variables to their types. But you present it maybe we present them as lists like this. So what is the judgment forms? There are two judgment forms. One says in a given context gamma, some term t has a type A. And the way that you read this is in context gamma. So the context tells you what variables are valid, what variables you may use. In context gamma, the term t has type A. And the other judgment form is t equals u at type A, and this says, the way you read this, in context gamma, terms t and u are equal at type A. So you have to also indicate what the type is. This is also sometimes written as t and then the equal sign is here, and sometimes the type is forgotten, but I do not recommend doing that, at least not in this version of the calculus. If you're going to have equality without indicating the type, you suddenly have to be a lot more careful. It's easier to make mistakes. Okay, now come the rules, because see, so we have syntax explaining what your syntactic expressions look like, and there might be several classes of syntactic expressions, so terms and types. Forms, judgment forms. What is it that we will assert? Because we could assert the truth of a proposition, we could assert the fact that a construction has been carried out, that an element of a type has been built, and this is precisely what the first judgment form is saying. But there are other possible judgment forms in general. In computer science, for instance, you might have a judgment form which expresses something about how a step of communication happened, or that a transition system made one step from here to there. All kinds of judgment forms are possible, not just what you see in first order logic, because in first order logic everything is just about formulas holding, being true. Right? Okay, so the judgment form, the other judgment form is about equality, so the things are equal. So this is what gives life to the calculus. If we didn't have the second form, if you just had the first one, then all we could ever observe is that we built some terms, right? We built a term. So that's like saying, you just build stuff from Lego blocks, and that's good. You're gonna have lots of stuff. But what equality does is it reveals the structure. So you might observe, for instance, that there are two ways to build the same Lego gadget. You could build a house by starting on this side and go there, or this side or go there. So there might be some, or for instance, you might discover that if you've built a little Lego house if you remove the roof and turn it around and you put it back in, that it's still equal because the roof was symmetric. And that would be an equation. You have now discovered some relationship between two constructions of the same Lego house. And that's what gives the lambda calculus and in general calculi a lot of punch, because it brings in equations. Equations bring in laws of reasoning, and they bring in structure, because you can start thinking about what is the structure of what I'm doing, with what are they describing. I mean, I think this should be obvious if you've ever been in an algebra course, that this is an important thing. Okay, so you might ask, well, where is computation here? Okay, because I have equations, I have stuff with equations. That's algebra, that's not equations. This is a presentation that is closer to algebra. However, it just so happens that the equations that we are going to write down have a particular form. So that particular form is such that if you read equations from left to right, they look like computation rules. So there are steps of computation that you might want to perform. And well, not all of them. Some of them are a bit fishy. They don't look like that, but the important, most of them, half of them do, at least half of them. And if you take those, they will induce an evaluation relation. So there is a third thing which I'm not going to talk about here, but anybody who's doing a little bit of programming languages in the project will face this question of how do you compute. And the answer is you give a relation which says this computes to that, this computes to that. And it's already hidden in the equations that we will look at, but it's not explicit. Okay, what are the rules? Well, now we're going to have rules, and we might as well have a look at the rules. I think this review will have all of them except for sums. So we're going to go through the rules here. See, this one, it doesn't have sums and empty, but it has the rest. So I think usually the lambda calculus is not considered to have sums. So what you really, really want are products and arrows, and sometimes only arrows. It depends. It's really different kinds of things. Okay, so what are some rules? First of all, every constant has to have a type assigned to it. So whenever you introduce a constant, you also have to explain what its type is. So if I introduce 0, I have to explain what 0 is supposed to have a type, what type is it supposed to have. Note that the type need not be primitive. For instance, successor has the type nat arrow nat. So that's not a primitive type, even though the successor itself is a primitive constant. Then there is the rule for variables, and the rule for variables says, well, if I have a context of variables, then the ith variable has type AI. So I can always look up the type. I look up the type. I see, oh, I have a variable here. Okay, that means that variable has that type, and I get a judgment. Then the constant star. Okay, apparently it's a star. What was it here? You'll survive. Okay, star, instead of the close bracket, open bracket, has type 1. So the notation here is, let's write it down here. So it's a slightly, I don't think you will, this is not, this subject is like, it's young. It's like from 1930s. So the notation hasn't quite converged as much as it has in analysis, where unfortunately it has converged. So now we can't change it, even though it's unreasonable. It's from the 17th century. So here we also have star and 1. Okay, and probably pi 1 and pi 2 might be something else. We'll see. Yes, they're called first and second. Okay. So here are now the rules for pairs. If U has type A and T has type B, then the pair UT has type A cross B. I can do this. If T has type A cross B, then first of T has type A, and second of T has type B. These are not surprising, I hope. Then we have functions. So, okay, if we have a term T, which is a function from A to B, and we have a term U of type A, then T applied to U has type B. And here is the lambda abstraction. It says, if you can write some term t of type b, but you're using the variable x, then without the variable, you get the function from a to b. Yep. Then we have equations. Well, what are the equations? The equations will say equality is an equivalence relation. So t equals t. This is like the last time when we had the predicate calculus. Reflexivity, symmetry, transitivity. Then I find this rule odd now. This has been like 10 years since I last looked at this. I'm pretty sure this rule is not necessary, but you will recognize the weakening rule, a special case of the weakening rule from your exercises, which says if you can prove something without a variable, then you can just prove it with a variable. But this seems wholly unnecessary, and is an interesting question of why I thought that this needs to be added here. The unit type, so I would recommend removing this stuff here. The unit type says, the unit type, okay, so now we go down the list of these types, and we ask for each one of them, what are some equations that we want? And we're going to get equations except for empty and plus, which we have to add them because these nodes don't have them. Okay, so the equation for the unit type expresses the fact that the unit type has just one element. So it says t, by the way, in these equations, we assume that the left-hand side and the right-hand side, oops, this should be an A, sorry. Okay, I need to fix this. That they're both of type A. We only ever compare terms of the type at which we're comparing. So any term of type unit is equal to star. That's one possible equation. And then we have equations for product types. Let's see. Pairs are equal if their components are equal. If pairs are equal, then their first projections are equal and their second projections are equal. So this all looks nice. And then we have this one, which says if you take a pair and then you take it apart and put it back together, you'll have the same thing. It'll be again the same pair. These rules here, the first three, these rules just say, okay, so let's have a look at all five and then we'll discuss them. So the second one says if you take the first projection of the pair ut, then that equals u, and the second, if you take the second projection of ut, you will get t. Now there are three rules here. I think I want to discuss these by taking them to my, but without this blue stuff. Blue stuff, go away. It doesn't want to go away. What happened? Once you have blue stuff, you can't get rid of it? Okay. No, not that. That. There's something here to be said about these equations. That's why I'm doing this. Okay, so if you look at them, you will see that, let's be careful about what their form is. These three here are, in a way, completely uninteresting. Because what they're not really saying that much. I mean, yeah, of course, if u equals v and s equals t, then when I form pairs, right? Functions preserve equality. This is just saying when you apply pairing, it preserves equality. And same here. When you apply first, it preserves equality. So in a way, these guys are a little more boring than the other guys. And these are known as congruence rules. Why? Because what they're expressing is that all the term formers, first, projection, second, that they are congruences. In general, that the quality is a congruence. Instead, in general, in algebra, what is a congruence in algebra? If you have an algebraic structure, such as a ring, then A congruence is a special kind of equivalence relation on the ring. Namely, it is an equivalence relation which respects the operations. So that, for instance, if A is equivalent to B and C is equivalent to D, then A plus C should be equivalent to B plus D. That's a congruence. That's the name that comes from algebra, and it's used in algebra that way, congruence. So what this rule is saying, what these rules are saying is that equality is a congruence with respect to all the syntactic operations. When you apply the same syntactic operation on equal things, you will get equal things. And they're always in the background, and they're written explicitly here. And in many textbooks, they will forget to mention them, or they will say, yeah, it's understood that they're there, but they're written out here. Now, the second batch of rules are the computation rules. And these guys are the interesting ones. And in this case, we just have this one. Okay, so this guy here, no, sorry, that's not the computation rule. This is a different guy. So this one, okay, let's do the computation rules first because they are, and we should have a break soon. I'll just do this product stuff and then we'll have a break. And then we have these two. Okay, so these two are computation rules. And you can recognize computation rules. You can recognize them because they will also be called beta rules sometimes. And if you know history, but only if you know history, you will call these sometimes Psi rules. Don't do that because nobody does that. Everybody's too young for that. So, computation rules you recognize because if you read them from left to right, they look exactly like what you would do in a programming language. Yes? So, if somebody says, how do you expect things to compute? Then this rule up here is useless. It's not telling you how to compute, right? It's telling you when things are equal. But this one here can clearly be read as a computation step. If I have first of a pair UT, then I can do something useful and I can make progress towards some sort of a final value. I just have a U here. The last one, here, this, oops, no, I failed. This thing here is called Ita Rule. This is from the 1930s. People really liked Greek letters, you know. So Ita Rule is, there is a related rules which look slightly different, and I hesitate to call this Ita Rule because somebody's gonna get on my case when they see this video. Extensionality rules are related. But it's a different form of rule. So for this one, it would actually look like this. It would say that if first of t equals first of u and second of t equals second of u. I'm leaving out the gammas. Then t equals u. This is at a cross b, this one is at a, this one is at b. And it turns out that these are related, interderivable, if you have the computation rules and congruence rules. So they're related, but the point is that I can explain the extensionality rules much better than the Ita rules. So the extensionality rule says things are equal when they have equal parts. Okay, and then this thing here says a thing is equal to being constructed from its own parts, so which is kind of similar. Okay, this is an important pattern in computational calculi, this kind of organization of equations. So once again, congruence rules are in the background. They're always there. People don't even mention them. Then there are computation rules, which give you a programming language when you do them right. If you do them wrong, you get a mess. But if you do them right, you get a programming language out of them. And then there might be something called Ita rules or extensionality rules or some such, and those are always debatable. Those always turn your programming language, they shift it a little bit towards these things being more like mathematical objects and less like programs. And that shift can be very important. It is very desirable from a mathematical point of view that your programs start to behave more like, you know, numbers and not some strange thing, or pairs really are pairs. They're not some strange thing that you can't get your hands on. So they are often desirable. We have seen this in the exercises. Function extensionality is an extensionality rule. Function extensionality says if two functions are made of equal parts, then they're equal. And we already saw that. So, but there it was even a stronger extensionality rule. I'm not going to get into the details of what was going on, but there it was expressed in terms of the identity type, so that's even stronger. I just wanted to say there is a system to the madness. People don't just jot down random equations and then hope that good things will happen. That's not how it works. Just like in algebra, why is everybody so keen on associativity in algebra? Well, they probably have a good reason for it, right? So it's the same here. Okay, let's have a break for 15 minutes and then we're going to continue. And yes, my battery is almost gone. Bom pisar, né? Okay, we have the charger, we have the coffee, we can go on.
Need the door?
Please close the door, yes. I think. Are those unruly financial mathematicians?
No.
Okay, so now let's have a look at the other things to see whether this pattern gets repeated. So we have function types. How do you get rid of the selection? Command Shift, let's see, Command A, Command Shift A, Shift A.
It doesn't work if you just hold down the mouse button and drag it just a tiny bit.
Now I can't get rid of anything. Wow, select all. Where is deselect? Help, help. Okay. Okay, how about these guys? So, let's have a look. You will tell me for each one of them. The first one, what kind of a rule is it?
A congruence.
Wait. I'll copy and so we can then write these things. Okay, so let's observe. So this one is congruence, right? That's just a congruence. It says that application preserves equality. This one is congruence because it says that lambda preserves equality. By the way, I wasn't stressing this, but x is bound in t. X is a bound variable here. What is and isn't a bound variable is a separate discussion, so I'm not going to get into it now. Okay? Well, unfortunately, here it reveals what is what, right? So let's just at least look at this and see whether we really can understand this as a reasonable computation rule. If you read it from left to right, it says when you have a function applied to an argument, you stick the argument into the body of the function. That's all it says. So it's a reasonable computation rule. And this one here is called an Ita Rule. And it says that if you take a function apart and put it back together, you get the same function. So, right? Applying t at x means you're taking it apart. You're taking a little piece of your function, one value at one argument, and put them back together, and you get the same function. Is this a computation rule? Like, would you read this from left to right or from right to left? It's not a reasonable computation rule from a programming language point of view. you certainly wouldn't read it from right to left because it makes things bigger. You'll just, you see, if you would take t and then you would go here and you would make something slightly larger and then you would apply it again. So that's not a good idea. From right to left is not a good idea because you would just use it all the time. How about from left to right? Well, it's weird because it means that you are looking inside a function to decide whether there's something that you want to do. And that's not a good idea. Okay? Because that means you have to start computing things start computing things in the body of a function, even before the function was called. Just as it was defined, you already have to start computing inside the body of the function. That's unreasonable. So that's not going to be a computation rule, just from a programming point of view. Okay? Now, that's the rules, but we threw in empty and sums. So let's do empty and sums with our bare hands. Okay, so let's first do empty. The empty type you go and you look at the rules for the empty type. We don't have anything, so we have to do everything. Okay, so what are the rules for the empty type? So the first one is that, okay, so the idea is that you want to say that the empty type is as empty. How do you say that something is an empty type? If you can't negate things. You can't say it's not the case that it contains things. You just have to say something. So what you say is it's as empty as everybody else. So how do you say it's as empty as everybody else? Let's first do a simpler example. Suppose you have a partially ordered set and you want to say that it has the smallest element. Well, the smallest element is the element that is as small as anybody else. So you're going to say bottom below x. So for the empty one, you want to say there's always a function, there's always a way. If I have something in the empty type, I can get something in some other type. That means it's as empty as anybody else. So how do we do this? Okay, so we say if you have constructed t of type empty, then you get to construct anything in any type whatsoever. You get a special element called absurd that gives you something of type A. This says, right, it's empty is as difficult to, it's the most difficult type to inhabit. If once you inhabit empty, you have inhabit everything else. Okay, that's the only rule we have because we just have absurd. Now, there is no way to actually construct elements of empty type. So how are we ever going to get a T like that? Well, we're going to get a T when gamma is non-empty, right? You can get T by having hypotheses that allow you to create T. For instance, T could be a variable of type empty. That would be one way to get it. What we should worry about is whether we can get a closed term of type empty. So is there a term of type empty in the empty context? That would be a little surprising. That would probably spell trouble. Okay, so how about equations? Now the equations here, the equation is a bit unusual. Okay, so first there's the congruence rule, okay? Congruence equation. So equations, congruence rule, plus, okay, so I'm not going to write it down. You can guess what it is. What do we do with this? What is an equation about absurd? How do you say something useful about absurd? By the way, this is not, if you say if t equals u, then absurd of t equals absurd of u, that's the congruence rule. So I'm not asking for that one. I'm asking, is there another one? And it says, it sort of has to say something about what happens with equations once we have an element of the empty type. Well, if we have an element of the empty type, that's a rather unusual situation to have an element of an empty type. That should just essentially, it should imply anything, right? So what we write is absurd a t equals u at a. This is super weird because it says that absurd t is equal to everybody in u. Now imagine that a is the natural numbers. If a is the natural numbers, this is going to say that this absurd business is equal to 0 and to 1 and to 3 and to 4. So everybody will become equal if you do that. Yes. But that kind of makes sense because if you manage to produce an element of the empty type, you're in deep trouble. So you might as well admit that everything equals everything, and then you say, okay, we're done. Yeah? So this is the idea. Let's also look at this from a categorical point of view. Okay, this absurd business. So if you know a little bit of category theory, you should contemplate about the fact that this is saying that empty is the initial object. But I'm not going to go deeper into that. Let's do sums. Oh, is this a computation rule? What is this? It's nothing, right? I mean, it's just strange. And it's from the point of view of computation, it's strange because we have no experience with computing with the elements of the empty type. There are no elements. See, you never compute with variables. You only compute with closed terms. If you have a program with an undefined variable, your programming language is going to complain because it doesn't know what to do with an undefined variable. It only ever wants to compile and run programs where all variables are bound, no free variables, no hanging free variables. So, because there are no closed terms of type empty, we have no experience on how to compute with it, and that's why it looks odd. So the best way to understand the empty type might be in terms of algebra or category theory. Agda can have the empty type, right? So you should be able to ask some embarrassing questions to the Agda designers about equations involving the empty type. For instance, are all terms of the empty type equal? Does Agda know that? Those are good questions to ask. Okay, sums. How about sums? Well, so for the sums, we're going to have first the obvious things, which are the injections. So if I have t, which is of term of type A, then if I do the injection, iota 1 of t, it will go into A plus B. And if I have t of type, well, let's write u here, u of type B, then iota 2 of u has type A plus B. And then we have the case business. The case business is going to be weird. Okay, so let's see. How are we going to give a type to consider what t might be? If it is of the form iota 1 of x, then you should do s. And if it is of the form iota 2 of y, then you should do u. And then the whole thing will be, say, of some type c. Okay, so how do we do that? So we expect this t to be an element of the plus. So it's going to be gamma t is of type A plus B. That's what we're casing on. Okay? And then this x here will presumably be from A. So we're going to say when we want the type of S, we're assuming that x came from A. And in that case, S has to be of type C. And similarly here, this y has to be of type B. And then u has to be of type C. We're calculating something of type C. So that's the rule. Equations? Any questions about this? Equations? Okay, congruence rules. Anything else? Well, a computation rule probably, namely, what would you expect happens if I do this? Case iota 1 of S of, no, let's do t here, of iota 1x goes to S, iota 2y goes to u. What would this be equal to? So this is saying, consider this thing. If it's of the form iota 1 of x, then you do S. And if it's of this form, you do that. Well, clearly we're going to do S, right? We're matching this against this, it matches. So this is S, where I replace X with T. And this clearly looks like a computation rule to me, because this is how you make progress, and this is how case statements are computed. You can have one more rule, of course, which is symmetric. You just have to do a little bit of editing here. No, eventually I'll succeed. And there we go. And then here it's going to be different. Case iota 2 of t, that's going to be u t for y. Like that. Is there an Ita rule? The Ita rule has to say, if you have an element of a plus b, and you take it apart and put it back together, then you're going to get the same thing. Okay, let's try to do that. If I have an element t, how do I take it apart? T comes from a plus b. How do I take it apart? Well, there are two cases to consider. If this t is of the form iota 1 of x, well, that's how I took it apart. Now I took it apart, yes? And then I have to put it back together. Well, this is how I put it back together. But if my t is of this form, then how do I put it back together? Well, like this. And we would expect this to be equal to t. And once again, we get something that's slightly weird, that is not really clear whether we want to compute with this thing. Okay, so that was the lambda calculus. The notes have other examples, like if you have natural numbers, you throw in 0 and successor, but we have seen these things before. Why are we doing this? Because it's a fundamental calculus that inspires lots of programming languages and stuff like that, but also because of the things that I have been writing here, hopefully remind you of the propositional logic. If we look at, let's see, did we have them somewhere? If we look at the rules of propositional logic, well, unfortunately, these are written in Agda, but let's have a look anyway. This one says, if a formula appears among the hypotheses, then it holds. And it reminds you of which rule? It says, if something appears in a list of hypotheses, then you get it out. Well, that's the variable rule, right? It looks a lot like the variable rule. So how close to the variable rule is it? Well, if we're quite exact, here, this thing here is a proof that the formula appears in my list, which is defined up here somewhere. It's this one. It's this weirdness. It says I have A, an element of A, and I have a list, and I want to know whether this A appears in this list. And if you look at what are the elements of this, there will be of the form there, here, right? And they will give you the positions where this A appears in the list. There will be exactly the positions at which it appears. But those positions are more or less like names of variables. So in fact, here, in a hidden way, the variable rule has also the position, which then corresponds to the name of the variable, and so that seems like a pretty good match. In fact, all of the rules will be like that, except the structural business here is not going to appear in our lambda calculus, because we never said that you can reorder variables or anything like that. There was some unsuspicious weakening rule, which I still have to think about why I thought it was necessary, but it doesn't matter because these rules are admissible. We discussed this last time that we didn't really need them. It's just that logic books have them. But you could just throw them out and you will be able to prove. You have to be a bit careful how you say it, but yeah, it will be admissible. Okay, so how about the other things? So does this remind us of anything? This just says there is something of this type. Well, that's the unit That's a unit type. It says star is an element of unit. So what's happening is that this thing here, it looks like it's like half of the unit type rule. Let's have a look. What was the unit? Or let's have a look at the more interesting one. Let's have a look at the conjunction here. Okay, let's compare these with the conjunction. Okay, so where were they? Oh, they are in the PDF file. Actually, I'll do it like this. Let's go and do this systematically. Okay, so first of all, we have the judgment form. So the judgment forms, so this is now propositions as types. It's a correspondence that shows that the two calculi that I described are essentially the same calculus. But how? Okay, so first we had propositions on one side, so propositions, formulas. Here we had type. Then here we had term. Is there anything that corresponds to a term? Yes. Proof. Except that while we wrote down terms here very carefully, we didn't write them down so carefully on the other side. So here we had things like, you wrote something like the second of the pair of variable lambda y a y, something like that, okay? Say in the context where x has type b. So we wrote this stuff, and then this is what? A arrow A. It has this type. And then here, where did this thing appear? Did it appear anywhere on this other side? This thing here? Yes, it did. It's the tree. Yes, it was hidden in the tree. So when we do this corresponding thing here, we would say under hypothesis B, we can prove A arrow A, and then here we said, well, it's the elimination rule, which one? The second one, elim 2, and then we would build on this, and we would say, but here now we're going to have B and A arrow A, and then here this is intro, and then here we have B and hypothesis, and then here we have A arrow A, and then we have, I want to actually spell it out once, intro, and then B, and then it's B A, and then it's a hypothesis, like this, okay? So what is what? Let's see how many colors I can use. So I'll use this color. Okay, so this guy corresponds to this guy. This guy, no. This guy corresponds to pairing. See? Then the lambda is the intro. Then the hypothesis is the variable. Big dot, who cares? Okay. Then I need one more color. Hey, why not this one? This other one corresponds to the other variable. It's an exact match. the applications of the inference rules correspond precisely to how this term is built. That's what it means that terms are proofs. This correspondence is exact. The difference is that here you see the derivation as a tree, and here you see it as a term. Well, then we have judgments. Let's see, what about the judgment forms? Judgments, well, this one has the judgment form that in gamma, in some, given some hypotheses A1 to AN, B is entailed, whereas this one has the judgment form given some variables x1, A1 to xn, AN, some term T has type B. And here the judgment is that of course there is some sort of a derivation up here. So the correspondence is, again, this derivation corresponds to the term, okay? Then obviously the types match, the type. And also these guys here match those guys there. But what about the variables? What happened with the variables? Where do they fit? Well, the variables fit because these variables here correspond to referencing a hypothesis, which is not really visible here. It's not visible here, it's not visible here, but it was visible in Agda. Because if we want to be completely sure about, we need to still check that A actually appears in this list. And how do you check that A actually appears in this list? You go and you give a position, which is the same as saying which variable you mean. Yes. So this is also okay. These guys here are, these are positions of hypotheses. In the context. That's what it is. In fact, there is a version of the lambda calculus where you don't have variable names. You just use positions all the time, and then that's called De Bruijn indices. We have Egbert here, who is Dutch, who can pronounce this in some way that I can't, well, no quotes, they're actually called that. De Bruijn indices, some of you will want to know more about this, and it's in the PLFA book, Phil Wadler's book. It explains this. It does this carefully to go from names to De Bruijn indices, is use positions instead of variables names, instead of variable names. It's like a step in compilation. The programmer gives the variables nice names, age, weight, price. But then the compiler compiles this and it says, oh, it's the first position, second position, third position on the stack. That's what's going on. We're doing theory, but we're doing useful theory here, okay? It's not just idle curiosity. So you may want to read about this in the book. Okay. So this correspondence is called propositions as types. There is one thing I have ignored, which is these guys here, well, they also have equations. What about those? There are equations here. What would that be? Well, that would be equality of terms, so that would be equality of proofs. But logic books don't discuss equality of proofs. It's a blind spot. It just doesn't happen. Yes? Even though logicians, when you speak to them, say, yes, we know we should do this, and it's interesting and it's important, but, and then the book doesn't say anything. However, type theory does address this, and so there has been some progress made here, and in the last, I will talk about it later on, to say what happens with this, because you have to say something here. I mean, if you're honest, you should say something. You could also just ignore the question and pretend that it didn't happen. But it would be a good idea. There are other things. For instance, here we said, oh, you can take all the beta rules and compute with them. Compute with terms. What's that here on the other side? Do we compute with proofs? Well, this is interesting. You see, traditionally proofs have this strange status in mathematics. I like to say that mathematicians think that proofs are irrelevant because they don't consider proofs to be mathematical objects. Like, honestly, they don't. If you go to the 4th floor, you like knock on somebody like algebra, geometry, and you say the space of proofs, and they will just go like, what? Yeah, there's no space of proofs. And this is always a good indication that something is being ignored. For instance, in the 17th century or the 18th century, you couldn't say the space of functions. You couldn't say that. It wouldn't work. It would be like saying the space of proofs. Yes, it just didn't work. It was the mathematics wasn't ready for it. But nowadays, of course, we know there are spaces of functions. You know, compact open topology, supremum norm on the continuous function, functional analysis. It's a big thing. Okay, so yes, so that's an indication that something is missing there. Okay, so mathematicians don't really consider proofs to be, it's just this stuff that you write in LaTeX to gain fame or something. It's not really math, right? So that's not good. But if you use a proof assistant, it'll force you to think about proofs, and you will start saying, oh, this proof is nicer. Say this proof is shorter than the other one, and then one day you're going to notice that proofs can be manipulated. And once you notice that proofs can be manipulated, you're going to say, but what are the rules of manipulation of proofs? And then you will, of course, start to actually believe in propositions as types. That will be the point where this has been not just something that your professor told you about, but you've internalized it, and you will say, yes, proofs are real mathematical objects, and we can compute with them. Actually, to be honest, a book on logic does have a name for this. It's called proof normalization. Thank God that logicians at least think that proofs are mathematical objects, and they do manipulate them, and they know that there is a thing called normal form of a proof, and they know that there is a process which takes a proof and turns it into this normal form, whatever it is. And that corresponds very precisely to computing with terms and reaching the final result called value. Okay, so it's exactly that. Okay, now, that was propositional logic. How about predicate logic? What happens with predicate logic? I referenced a bunch of sections in various books where you can read about propositions as types going all the way to propositional logic. I will give here a brief overview. I'm not going to do this now in the same kind of detail that I just did for propositional logic, but what about propositions as types for predicate logic? The main difference between propositions as types between propositional and predicate logic is that in predicate logic there are predicates. So let us recall how that was done. First, we had terms and individuals. They're called individuals. Now, often people say that often people do single sorted predicate logics, but let me just say that there will be some sorts, A, B, C, and so on. And then there will be some terms, STU elements of these sorts. And then there will be logic on top of that. So there will be predicates. What will a predicate be? Well, a predicate in general will be something like phi, which takes in a term like that. So this is going to be a term, and this is going to be a formula. And then there will be rules for building these predicates. So built from, we had this last time. I was reviewing the predicate logic, if you will remember. Well, equality was one of them. You can make, of course, you could have more here, right? You could have several. And then it's a ternary predicate, also called a relation. So there will be equalities. Then there might be some primitive predicates. So what would be an example of a primitive predicate? Suppose we were doing Euclidean geometry this way. If we did Euclidean geometry, oh, maybe I can have an example here. Euclidean geometry. Well, the sorts would be points and lines, because that's what we would talk about. Later on, we would face the question of what to do about circles, but at least at the beginning, we're going to say there are just two sorts called point and line. And then the terms, well, there won't be a whole lot of terms, but the terms would be the ones that you can, for instance, they would be the points that you can construct using compass and ruler. These are used to construct terms, to construct points. Then there would be some predicates. What will be the basic predicate? The basic predicate will be here, down here, primitive predicate, will be a point lies on a line, right? A point is on a line, so coincidence. Point P is on line L. That will be a basic predicate, which I would write using this symbol, but then everybody will think I'm doing set theory, so I will refrain from doing that. Okay, so then there's logic, and we already know what to do about this stuff here. But more interestingly, there will be this and there will be that. And this is what we want to know. What is up with this? So which are the new parts? These are the new parts. These are the new parts. What do we do with these things? Okay. The answer is we pass to dependent type theory. We're now not going to have just simple types. Oh, by the way, simple types correspond to atomic formulas. Like the primitive types, the primitive simple types correspond to atomic formulas. But now things will become dependent because predicates, which use formulas, are dependent on terms. So that's why we have the dependence. So the new picture is like this. Here we have a formula. And so in general, you're going to have a formula that looks like this. You're going to have some variables of some sorts. And then you will form a formula phi, which depends on these here. That will be some sort of a formula. I'm not saying that it's true, I'm just saying it's a formula. So that on the here, this will be a dependent type. And you should be familiar by this because it shouldn't strike you as totally odd because we've been doing this in Agda all along. So it's going to be a type which depends on these A1s and to ANs. So it's going to be something like, phi maps from A1 to AN to types, if I can write it this way. Much of the rest stays the same. It's still terms or proofs and so on. There's just these new additions that we have to pay attention to. So what are these new additions? One of them is identity, equality, t equals u at some type A. That's going to be the identity type. id a t u. Then there will be, in logic, there's an addition of new things. So for all x in A, phi of x, that's going to be pi. And exists is going to be sum. This is the traditional propositions as types correspondence, which has been very, very fruitful in theoretical computer science in developing various kinds of logics, because this gets extended in various ways. For instance, you can ask, what if the logic is classical? Can I still do it? What if I have model operators? Can I still do it? What if I throw in something else? Can I still do it? And so on and so on. I'm not going to drag you through these. I'm not going to drag you through these rules. Maybe we have a look at one of them. There's going to be 4 rules here: the introduction and the elimination of for all, the introduction and elimination for exists. So let's have a look at exists, how you do exists. What is the introduction for exists? The introduction for exists says that if you have, so now I have to be careful because I'm going to have variables. So let's have some contexts. I'm going to have a context gamma of variables. But then I also have a context delta of hypotheses. Remember last time I had several of these. And then the rules go like what? If I have these variables and I have these hypotheses, and I have successfully constructed a term T of some type A, and then I prove that this term T satisfies the property T, then I may conclude that there exists some X of type A such that phi of X holds. So this is Ita Rule. Let's read it again. You construct a particular individual T of type A. You show that it has property phi. You may now conclude that there exists something of type A satisfying the property phi. That's the introduction rule. Okay, what's the corresponding rule on the other side? The corresponding rule on the other side is going to be the introduction rule for sigma. What is the introduction rule for sigma? But now, first of all, this context, it all just becomes, everything becomes the same. Here, we need to distinguish the context of individuals from the context of hypotheses. This is, in fact, a worthy observation. Logic is stratified. At the bottom, you have individuals, terms, points and lines, stuff that you're going to talk about. On top of that, you have logical formulas which say things about the individuals. That's how logic is structured. Type theory is not structured like that. In type theory, there is no distinction between logic and the natural numbers versus a formula. They're both types. So you just get to mix them in arbitrary ways. So whereas here we have separated the contexts because of this stratification, hypotheses are stratified. What individuals are hypothesized and what truths about them are hypothesized versus stuff is hypothesized. So you just put them together here. Okay, and so then you say, if you produced a term T of type A, and you also produced some proof U of type phi of T, then you may form a proof Tu of sigma xa phi of x. And in the nodes that I linked to, you will see that all 4 rules work out this way. Now that you've seen one of them, the rest is technique. Observe that this is really the same structure. The only difference is that here, in type theory, I write the proofs explicitly. in this place. And I don't distinguish between constructing an element of a sort and constructing the proof of a type. I don't distinguish. It's just construction, which is yet another way of saying that proofs are mathematical objects. Mathematicians honestly believe that there is something worthy about computing the limit of a convergent sequence, and they think that they have constructed something. For instance, pi. You can write a paper about pi is the limit of some sequence. It's okay. But they never observe the fact that proofs have the exact same status as constructing a real number. You construct a real number, you write down the proof, it's the same thing. Both are constructions. So that's what type theory is telling you. Both are constructions. Here, interesting phenomena will happen. You can now, in type theory, I can start mixing stuff. I can say, I have a bunch of variables for individuals, then I have a couple of hypotheses, then I have more individuals that depend on the hypotheses, and you will notice that that's how mathematical practice works. But logic ignores the fact that mathematical practice mixes hypotheses. So this is actually closer to practice. And this is why proof assistants use type theory, because if they use first-order logic, well, they've tried, but automated theorem provers seem to prefer this kind of thing, or maybe people just haven't yet noticed type theory. But it's certainly, in my opinion, closer to how people actually work. So we get the Curry-Howard correspondence also for predicate logic, and read about it. Where is it? Here are going to be some links. So this is the lambda calculus stuff. This is just Wikipedia. This is just like if you want to lose an hour, you click here and then you do the transitive closure of Wikipedia. But the hot book has a nice introduction, and then the PLFA has these things here. Okay, so we have one more thing to discuss, which is how come type theory speaks about equality of terms, but logic doesn't speak about equality of proofs. What is there to be said there? Okay, so that's the remaining bit. And again, we have a 15-minute break. Okay, let's do a little more. Now we are actually getting kind of close to the present. The untyped lambda calculus is what? Early 1930s. The typed lambda calculus must be around, I'm going to go on a limb and say 1940 or so. I should know these things because the lambda calculus was invented by Alonzo Church, who had a student, Dana Scott, who had a student, which is me. So we are discussing things that my academic grandfather did. So I don't know the exact years, but say it was around, it must have been around 1940 with the simply typed lambda calculus. Now we're going to discuss things that were, then the Curry-Howard correspondence, this one, okay? The Curry-Howard correspondence in this form. That, I think, is already 1970s. So it did take quite a bit of time for people to realize the connection between logic and type theory. After all, type theory was formulated, this form of type theory was formulated by Martin Löf in the early 1970s, so the Curry-Howard couldn't really be younger than that. So 1970s, and now we're going to do things which got their attention, well, at the beginning of the 2000s, and then they really took off with homotopy type theory, which would be 2011 or so, something like that. So nevertheless, so what I'm saying is that this is fairly new stuff, okay? And it's also quite active research-wise. So what I would like to address is the background of some of these questions that I was asking and what to say about them. Okay, so let me do it this way. first, a point about logic, okay? When you have a proposition P, when you have some formula phi, it's a logical statement. To say, you can say that phi has a proof, in which case you say P is a proof of phi. This means that you actually produced one particular proof, P, which is witnessing that phi holds. Now, a related statement that you could make is to say that phi is provable. Now, provable means that there exists a proof, but you're not specifically giving one. You're just saying that there is a proof, but you haven't actually demonstrated a particular one. So that is a difference here. There is also phi is true, which is a semantic concept, but I'm not going to go into that today. That leads to questions of semantics. But let's concentrate on the difference between these two, because under propositions as types, we should ask, what is this? Well, if we're all, so these are both valid options on how we are going to think of propositions. This one leads to the idea that phi as a type, what are the elements of phi? So let me write it slightly differently. Okay, so on this side we have logic. On this side we have type theory. And as we said before, to say that P is a proof of phi, this led us to the idea to say that the elements of phi are the proofs. So if you subscribe to this first line, then what you are doing is you are really studying proofs. You are interested in what are the proofs of phi, which means that when you have two different proofs, you construct a proof, you construct another proof, you will observe and study the difference because there will be the different elements of phi, obviously so, because they look different, they're different trees. So that's one option. But this option here, when phi is provable, to say that phi is provable doesn't give you any structure. The only thing that matters is that it's provable, and that's all that there is just simple fact. So what really is going on when you say that phi is provable, you want to think of phi as with all the proofs crunched together into a single unit of provability. See? To say I study proofs of phi means, of course, I will distinguish different proofs. But to say I study whether phi is provable means I don't care what the proofs are. I just care that there are proofs. They're all equal to me because I'm only interested whether they exist. So this means that phi, the element phi, should have at most one element. So these are two different points of view of how you're going to study propositions, formulas. Will you study the proofs and their structure, or will you just study the fact that phi happens to hold?
Wait, I have a question. So
yes.
Shouldn't we have at least one element so that there is?
Well, let's make this a slightly more exact. Phi is provable. This should correspond to there is an element of phi, and phi is not provable, there is no proof, should mean there is no element of phi. Okay, so as soon as phi has an element, it's provable. So your question, you were now suggesting that there always should be an element, if I understood you correctly. But that will eliminate all things that are not provable. You see, the not provable phi's will be empty. So it's important to allow empty types. A type phi being phi not having any elements means you cannot prove phi. If we can prove everything, we just go home. I mean, there's no point to that. Okay? It might be interesting, a setup in which everything can be proved might still be interesting if we're interested in proofs. But if we're interested in provability and everything is provable, then there is nothing to do. There is no structure anymore.
I guess we're just confused why we have to limit ourselves to having at most one element.
Okay, I will give you another view of this which might help. Okay, so for a moment I'm going to back off and I'm going to explain something similar again, but this time not with all this heavy-handed type theory, but just with sets. And the idea is something that I think I mentioned it before already, and we're going to come back to it. And we're going to say this. Imagine the following story. Somebody said, okay, I want to do everything with sets. No logic. Just sets. No logic. No logic allowed. Everything is a set. And then they say, okay, but I mean, now that no logic is allowed, you need to somehow encode. You need to encode logic using sets. How are you going to encode logic using sets? And you have this bright idea that you say, well, empty set means false. And the set with one element, if I have a set A with one element, that means true. Why? Because when you do that, something very nice happens. If I have, so what is this together? Together, this means sets with at most one element. The empty one and the singletons. We take them all, okay? They are going to have a magical property. And the magical property is this. A cross B will be acting exactly like conjunction. Think about it. If either one of these is empty, you will get empty. But if they both have one element, then the Cartesian product will have one element. Yes? Nice. But it will also work for this guy. Think about it. If these two have at most one element, then how will it happen that this is empty? Only in one case, when A has an element but B is empty, then it will be empty. In all other three remaining cases, it will always be a singleton. So we really can use sets with at most one element and set theoretic constructions to simulate logic. This is again just, well, this is not propositions as types. This is now propositions as sub-singleton sets. But it's working. Is it really working? Really, really working? How about OR? How are we going to do OR? It's not sum. It cannot be sum, because then you will get two elements. And that's wrong. Union? No, because I allowed all singletons. If I allowed if I just set a specific singleton, no, but I want to allow all singletons. So, well, we should fix it. We can fix it. We can fix it like this. You can say A plus B. What do you do if you have too many elements but you want to have just one? You take a quotient. You take a quotient which makes them all equal. So you say A plus B quotiented by the relation where x is related to y for all x and y. Because now, let's think. If a and b are both empty, then I get empty, and the quotient of empty is empty, so false or false is false. But if one of them has an element, or both, then I will get a set which has one or two elements, but then I will quotient so that I get the equivalence classes, and then again I will have just one equivalence class, and I'm done. So you could also do OR this way. The other option you have is you say, this is stupid here. Why do I want the singleton? I don't care if it's a singleton. I could just say, how about if I do this? This guy means false, and if A is non-empty, I don't care how many elements. That just means true. So false means empty set, but any non-empty set means true. So now it's all sets. Can I do this again? Yes, I can. I don't need to worry about the plus. Cartesian product, let's think about it. When is the Cartesian product empty? Well, the Cartesian product will be empty if one of them is empty, which is precisely what we want of conjunction. Functions work the same way. When is there no function from A to B? When A is non-empty and B is empty, which is precisely when implication should be false. Plus now is not a problem. I don't care if there are many elements. So this is another possible view. This one is propositions as types. Propositions. Well, it's really propositions as sets, right? We discovered propositions as sets. I don't know why nobody did this, but I mean, people know. If once you see propositions as types, you say, well, but this is just interpreting types as sets. So this is propositions as sets, but this is propositions as sets with at most one element. You could do that. And by the way, this of course is going to work for all and exists as well. Except that here you will again have to quotient, because when you take a sum of sets, singleton sets, you can get many. And here you don't care. So this is another view of propositions as types. If you start with sets, if you're in love with sets, you say, okay, I want sets. Yeah, you can have sets. So what I'm describing here are just forget the philosophy. These are just two possible options how we might mimic logic using sets. One would be use sets, think of empty set as false, all the non-empty sets mean true. This is of course now saying, well, but what do these different elements of A mean? And the answer is, these are the different ways of proving A. That's precisely what it is. It's just like before, when we had type theory. How about here? What does it mean? Well, now I don't have to ask what that element of A means. If it's not there, it means A is false. If it's there, it means A is true. There is no further structure. I can't discuss the elements. I might be a little bit bothered by the fact that there are lots of singletons. And I could ask, but why did you take all the singletons? Why didn't you take just one singleton? Wouldn't it be more economic to say, just take this and that? This one means false, this one means true. Why not this? Now I just have two sets. Here I had huge amounts of sets because singletons form a proper class. But now I just have two sets. Yes, congratulations, you discovered the Boolean algebra too. That is the third option. But it's just the Boolean algebra 2, which we already know. This is what I would say is logic engineering at its best. You need to free your mind and think about the possibilities, because you will discover interesting things, right? If you're too hung up with truth and what Carnap said and what Kant meant, yeah, it's fine, yeah. But this is just like math, the freedom of math. Okay. Let's go back to this. I hope I explained why this idea is interesting, that phi should have at most one element. If for no other reason, because we have this option. Okay, maybe it's a bit suboptimal because we're doing something weird with plus and exists, But it's mostly working. From a philosophical point of view, it's pleasing because it's replacing proofs with probability. It's allowing us to think about why a proposition is true without being obsessed with which proof. This is not a trivial matter, in fact. In mathematics, there is, in the practice of mathematics, there is definitely a difference between somebody saying, I solved this differential equation, here is the solution, and they write the solution for you. Now you have a concrete solution of your differential equation. This is different from using some abstract thing which says that every differential equation of such and such form by axiom of choice has a solution. In the end, you know that it has a solution, but you have no solution in your hand. These are two different kinds of existence. Existential statements in mathematics, in practice, some of them are proved in a direct way where you actually construct the thing that you want. But there are important cases where you don't construct the thing that you want. Nevertheless, you know that it exists. And I'm not talking just about proof by contradiction. This is not just about proof by contradiction, which is one way of constructing, of knowing that something exists without constructing. You say, suppose it didn't exist, la 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 la, contradiction, oh, therefore it must exist, but now we have no idea what it is. There are other forms of this. And these other forms are related to this difference. To say that you have a concrete proof of a set versus we took a quotient. Now everything is bunched together. They all look the same. Now we don't know which one. Right? I can't distinguish them anymore because I took an equivalence class of all of them, and so now it's silly. Yeah? Okay. So this leads to a different view, a more updated view of propositions as types, which is propositions as sub-singleton types. So that's an option that you can have in logic, where you say, let's have a new one, where we say the following. We say, not all types are propositions, because after all, it's kind of stupid to think that the type of natural numbers represents a logical statement. Let's be honest. How does the type of natural numbers represent a logical statement? It doesn't, right? We want it to represent numbers, not some truth. So it's a bit silly to say that all types correspond to propositions. It's doing something strange. So let's be a bit more careful and say only certain types represent, or since we're doing type theory, we just say are propositions. By proposition, I mean have a logical character, are logical statements. Propositions, logical statements. Which ones? Well, the ones with at most one element. So we subscribe to this view that says in type theory, we speak of provability of propositions, not proofs. So these are called, well, let's first write it down. So satisfying, how will I say in type theory that a type has at most one element? How do you say that a type or a set has at most one element, and you are not allowed to say it's either empty or a singleton? That is a horrible way to say it. That's excluded middle thrown in for no good reason. To say that you have at most one element, what is the simplest way to say it?
Every element of the set is equal to chapter.
Every element of itself, well, every two elements.
I mean, yes.
Any two elements.
Any two elements of that set are equal.
Any two elements of that set are equal. Or in Agda, any two elements of that set are equal. Yes? This is how you can say it. Now, this, because of homotopy type theory, is sometimes called H propositions. H for homotopy. Because there is a reading of the equality type which we haven't, the identity type which we haven't discussed, which is that you secretly think of types as spaces, and this is the space of all paths from X to Y. So what this is saying is for any two points in the space, there is a path between them. And that's where this homotopy business comes in. So H proposition, but often just proposition, which I think is a good name. Unfortunately, the notation prop is taken in Agda, so I will use hprop in my Agda code. But this is the idea. This is the idea that what we would do is this. So if we now look at, such types are sometimes, so there is a precursor to this homotopy type theory business, in which the types of this, in which truncation was written with bracket types, and so there's also sometimes goes as proposition as bracket types. Now, this idea that not all propositions are types, not all types are propositions, only some of them, namely the ones with at most one element, sometimes goes by this name because there was a paper by Steve Audi and myself about this, where this arose. Okay, so now, see, I was around in 2011. Actually, this was probably 2004, 6 or something like that. It's a precursor. Okay, so let's have a look at this, how we would do this in Agda a little bit. So we want to formalize the fact that only some things are propositions. Here it is. When is A a proposition? When for all points there is a path between them. Okay? So now, ignore this for a moment. Now we can define here the type of H propositions. Unfortunately, prop is taken in Agda. I think there's some way to rename it with a pragma, but I didn't bother. So H prop, what is H prop? It's when is a proposition, when is a type of proposition? Well, it is a type which happens to be a proposition. So the space, excuse me, if we define now, see we have in Agda notation, we have set was all types of level L, all types at level L. But if we want just these, what would you write? Well, you would write the following. You would say a type at level L such that for all x, y in A, x equals y. Or in Agda notation, well, sigma A, and then here it would be pi, well, the thing we already wrote a couple of times. Okay, but so you don't use sigma for this, you use a record type. So this is really going to be a record type, which has two fields. What are these two fields? Well, here's the first field, and here's the second field, right? This one is a type, and this one is the proof that the type has at most one element. Haha. So you could think of this as the proofs of A, and this is saying all proofs are equal. Okay. So that's why this record type here is called, has two fields. The first field is a type, and the field name is proof, because to have an element of this type means to have a proof of the proposition. And then the second field says, actually all the proofs are equal. The type of proofs is the type of proofs has the property that all are equal. Yes?
Sorry, isn't this contractibility?
No, because we know this would be contractibility if we also require that this thing has a point, but it could be empty. Yes? Okay, so this could be empty. And so then the empty thing, of course, satisfies the fact that all elements of the empty thing are equal. So it's a proposition. So this is how you could set up this new kind of logic where you use hprop. But now when you use hprop, for instance, when you define conjunction, it'll go from hprop to hprop to hprop, and this is for general universe levels. And then you see, you do propositions as types on the proofs. You say, if I have I have one type called P, another type called Q, I make P cross Q. But now, assuming that this says P has at most one element, this says zeta has at most one element, I need to construct the proof that then in that case also the Cartesian product has at most one element. And this works, but for implication you need function extensionality, as always when you have functions and you want to prove they're equal. But then what do you do with OR? You see, with OR we need to make these quotients when you get to OR. But Agda doesn't have such quotients. You can't make them. But you can axiomatize them. You can say, but I want them. Okay? So you can axiomatize them and say, let's have a construction that works this way. And this construction is called propositional truncation. It's an operation which takes a type A. So the idea is the following. It's exactly in set theory it would be this. You take a set, you quotient it by the largest possible equivalence relation. You take a set, define the equivalence relation on it, which makes everybody equivalent, then you quotient. Your brain, because you were raised classically, your brain keeps thinking, why is he doing that? Why doesn't he just say, if it's empty, then it's empty, and if it's not empty, then it's a singleton? I'm doing that because the construction then is structurally reasonable, whereas distinguishing cases like that is not that reasonable, structurally speaking. So, propositional truncation. The idea is that you take a type A, and then you form a new type, which is often written like this. And this is called the truncation of A. And secretly, I want to say, well, it's the equivalence classes. Okay, so what do you need? Well, you need, first of all, if it's going to be the equivalence classes, you will want the quotient map. So there should be a way of taking A and calculating its equivalence class. And this map is then written like this. It's the equivalence. So this is the equivalence class of A. Think of it that way. But of course, there can be at most one equivalence class, because our equivalence relation is the one that makes everybody equivalent. So we also need to say that all these equivalence classes are actually the same. Actually, we should say all the elements of truncation are the same. So what we need in addition is that we say is proposition. This, we want to say that, which means for all UV, for all equivalence classes, they're equal. Now let's have a look at this. We're not quite done here, but let's have a look at this much, and then I will just tell you what is still missing, and then you should, anybody who's interested in this should read about it. There are references, and also speak to people who have been doing homotopy type theory here, which is the two of you, right? They will be able to, so Matej, the background, they have done this, and so, invite them for a coffee, they'll explain. Okay, so here is the propositional truncation, which says, okay, given any set, we get a new set. Ignore the levels, don't worry about the levels. And then we want to say, ooh, this is weird. This should have, oh, this is super weird. This is missing, it's the wrong definition. This is missing the brackets. Okay, we should say that the bracketed A is proposition, because right now it's saying every set is a proposition, which is not so good. No wonder it was so easy to use when I proved things. This is the equivalence class of an element. It says take an element, produce something in the quotient, and then there needs to be a statement that this really is the quotient. Okay? And the way that you say that this really is the desired quotient is you say that you give a universal property plus universal property, because it's almost 5 o'clock. I will state the universal property, but then I will say what the point of it is. Okay, the universal property says this. Suppose, so here we have the quotient map. This is the map that takes an element and puts it into its equivalence class, which is the only equivalence class. Now suppose I have B here, and I know that B is a proposition, so has at most one element. Then I have a map here. Will I get a map there? The answer is you will get a map there. And in fact, you will get just one map there. So now you want to say here there exists some map. So for every f, there is exactly one f prime such that this commutes, such that f equals f bar composed with this thing. This is category theory. This thing has the exact same form as the basis, the basis of not the basis of vector space, but well, also actually the basis. The basis of a vector space, that a vector space is spanned by a basis. A is the basis. The bracket A will be the entire vector space. The horizontal line is the inclusion of basic vectors into the vector space. F is a linear map. B is a vector space. So the B has to have the same structure as the bracket A down there. Groups. A is a generating set for a group. Bracket A is the free group. B needs to be a group. Then the same thing holds. This is saying that we have the best, the most economical way of turning a set into a group, a basis into a vector space, a type into a proposition. That is why down B must have the same kind of structure as the A. So this is the universal property, and it's stated here somewhere. If B is a proposition and you have a map from A to B, let's have a look. If you have a map from A to B, then you get a map from the truncated A to B. It's exactly this. Okay. So I don't know. I suspect you are not going to, not many of you will actually need this, but I thought it was worth telling you about it, just in the interest of general knowledge. And on that note, I finished today 2 minutes early. You can congratulate me. 1 minute early. Serves me right.